Hello friends, welcome to UGC EPG Pathshala. I am Dr. Dilip Kumar, Assistant Professor in Geography, Shahid Bhagat Singh Evening College, University of Delhi, Sheikh Sarai, Phase 2, New Delhi. The current session is on insolation, factors and distribution. Under this session, we will discuss the source of solar energy, method of solar energy receipt, factor affecting insolation and distribution of insolation. Let us start the discussion. You must have traveled different places and observed about the temperature as well as precipitation condition on those places. You are also aware that the mountains are cool to cold and plains are warmer. If they exist on the same latitude, you must have observed that there is a seasonal change, and with this the temperature and moisture also changes. Based on temperature, the air pressure is also greatly affected. Differences in the pressure results in the wind pattern, but you ever thought why it is happening so? For this, there are several factors responsible. The changes are seen with reference to latitude, altitude, sun position, with reference to earth, nature of sky, etc. In this module, an attempt has been made to discuss the insolation in general and its factors as well as its distribution over the globe in particular. The source of solar energy. The sun is the source of almost all the energy for our earth except geothermal energy. The sun is the biggest star in our solar system and ranks as a center of our solar system. It provides all the lights and heat for the surface of the various celestial body in our planetary system. The sun's average diameter is 1391000 kilometer, which is 109 times bigger than our earth. Sun is a self-luminous sphere of gases that emits radiant energy. This emits energy come from the fusion reaction take place inside the sun. Under high pressure, two or more hydrogen atoms fuse together to form one helium atom. In this process, hydrogen bomb explosion type energy is generated. The fusion process is a continuous affair with the sun. Thus, the chain of reaction and continuous explosion releases tremendous amount of energy that radiate out from the sun in all directions, usually associated with terms such as coronal mass ejection. Solar flare and sunspots. The outflow of energy is absorbed to be at the speed of light. Earth's upper level atmosphere receives about 1 part out of 2 billionth of the radiation given off by the sun, but even this tiny amount affects the biological and physical characteristics of Earth's surface. From the outermost layer of the sun, ionized gases acquire enough velocity to escape the gravitational pull of the sun and became a solar wind. These solar winds produces by a stream of extremely hot proton and electron. Occasionally, these solar winds approaches Earth and intensify the auroras. The intensity of the solar wind is influenced by the sunspot as mentioned in the figure 1. Energy is emitted by the sun in the form of electromagnetic energy which travels at the speed of light in a spectrum of varying wavelength. It takes about 8.3 minutes of time for these waves to reach Earth. About 41% of the spectrum come in the form of visible light rays, but much of the sun rays energy cannot be seen by the human eyes. About 50% of the sun radiant energy is in wavelengths that are longer than visible rays, including some infrared waves. Although these wavelengths cannot be seen, they can be sometime be sensed by human skin. The longer wave is the infrared part of the spectrum are felt as heat. The remaining 9% of the solar energy is made up of X-rays, gamma rays and ultraviolet rays, all of which are shorter in wavelength than visible light. These also cannot be seen but can affect other tissues of the human body. Thus, absorbing too much X-ray can be dangerous, and excessive ultraviolet waves give us sunburned skin. Collectively, visible light, ultraviolet rays, X-rays and gamma rays are known as a short wave radiation. We have learned to harness some energy wave for communication, microwave transmission, health and the use in the field of remote sensing, as mentioned in the figure number 2, the receipt of energy. The Earth's surface and the atmosphere receives maximum energy from the sun in a form of solar energy to run their system, such as hydrological cycle or other atmospheric dynamic. The term insolation, that is in plus sol plus ation, is derived from the word incoming solar radiation. Insolation especially applied to radiation which is arriving at Earth's atmosphere first and then Earth's surface. The heat is derived from solar energy, normally called solar radiation. Similarly, solar energy received by the Earth is called insolation. It is amount of incoming solar radiation that is received over a unit area of the Earth's surface. Solar energy received over the planet's surface varies according to season, latitude, transparency of the atmosphere, aspects or the ground slope. Method of solar energy receipt. The solar radiation received by the Earth atmosphere and surface is direct radiation or diffuse energy. There are 5 ways of solar radiation. They are transmission, scattering, refraction, absorption and reflection. The number 1 is transmission. When the solar radiation reaches to the Earth's surface through a medium is known as transmission of solar radiation. The dictionary meaning of transmission is the passage of short waves and long wave energy through either the atmosphere or water, as you can see in the figure number 3. But sun energy is reached to the Earth without any medium from the space. It is also known as radiation. The atmospheric energy comprises short wave radiation input and long wave radiation output that passes through the atmosphere by transmission. In our atmosphere, all the radiation is not reaching to the Earth's surface, or in other words, atmosphere is not opaque for all the radiations. For example, ultraviolet energy is absorbed by ozone layer in the atmosphere, which is coming from the sun. The transmission of short wavelength and long wavelength can be understood by the example of car with closed glass window, where short wave radiation transmit into the car and warm inside the car and does not transmit back through the glass, causing very high temperature inside the car. Similarly, our Earth atmosphere easily transmit incoming short wave solar radiation, but it is poor transmitter of outgoing long wave emitted energy by the Earth's surface. This differential transmission causes the greenhouse effect in the atmosphere. Due to greenhouse effect of the atmosphere, the Earth atmospheric temperature is hospitable. Without this effect, the living condition could not be created. The average global temperature is 15 degrees Celsius is possible only due to greenhouse effect. Otherwise, without this effect, the average temperature would come down to minus 17 degrees Celsius. The scattering. Atmospheric gases and dust particles physically interact with incoming solar radiation through process of scattering. A redirection of energy through refraction and reflection is called scattering. The solid particle of dust, smoke, aerosols, sea salt, sprays, pollutant, atmospheric humidity, smoke, shoots, etc. available in the atmosphere are responsible for scattering of sun electromagnetic energy. It changes the direction of the light movement without altering the wavelength. This phenomena is known as scattering and represent 7% of the Earth's reflectivity or albedo. It is unpredictable because of multiple reflection of electromagnetic waves by particle and surfaces, but in reflection, the direction of reflection is predictable. Dust particles, pollutant, ice, cloud droplet and water vapor produce further scattering. The thumb rule is the shorter the wavelength, the greater the scattering, and longer the wavelength, the less the scattering. Small gas molecules in the air scatter shorter wavelength of light. Thus, shorter wavelength of visible light scatter more. It is due to greater scattering of these visible rays. The sky appears to blue. The angle of sun rays determine the thickness of atmosphere they must pass through to reach the surface. Therefore, direct sun rays from overhead has less scattered and absorption than low oblique angle rays because it travel further through the atmosphere. Insolation from low angle of sun experience more scattering of shorter wavelength, leaving only residual orange and red region. Wavelength appears orange to red at sunset or sunrise. Incoming insolation is diffused by cloud and atmosphere and is transmitted to earth. That energy is known as diffused radiation, where light is scattered to appear white cloud. This light is multidirectional and thus casts shadowless light on the ground. The refraction. Refraction means bending of light. As solar radiation enters the atmosphere, it passes from one medium to another of atmosphere from virtually empty space into atmospheric gases. The atmosphere itself is made up of different layers. The different layers have different density, and change in density of the atmosphere cause the bending of incoming solar radiations at different angles. This refraction could also be seen with water as well. It is known as refraction of incoming radiation. For example, prism refracts light passing through it, bending different wavelength to different angle, separating the light into different component of color to display the spectrum. In nature, rainbow is created when visible light passes through many raindrops and is refracted and reflected toward the viewer at a precise angle. Mirage is another example where an image that appears near the horizon, where light waves are refracted by different layer of air of different temperature in summer hot day. Reflection. The reflection is an ability of the material where a portion of arriving energy strikes depending upon the surface characteristics. Where it strikes, the quantum of reflectivity is determined. It might be completely bounced directly back into space with or without being absorbed. This return energy is called reflected, especially specular reflectance where angle of incidence and angle of reflectance is same. A mirror is one of the example of reflecting more than 90% of the visible light incidence upon it. The term albedo is used to describe the amount of energy reflected back in percentage. Albedo is a reflective quantity of a surface. It is the important control over the amount of insolation that is available for absorption by the surface. So, the proportion of the insolation that is reflected back from the atmosphere from the top of the cloud and earth's surface, including land and water both, without heating the receiving surface, is an albedo? Of the total insolation, about 30% average but varied widely according to the material and their characteristics of the surface as well as the angle and wavelength of the incidence radiation. The albedo from green grass and forest is 8 to 27%, more than 30% for yellow deciduous forest in autumn, for cities and rock surface 12 to 18%, more than 40% from chalk and light color rocks and buildings, for sand up to 40%, for fresh flat snow up to 90%, and for calm water very little, that is only 2% of in the case of vertical incidence radiation, but up to 78% where there is low angle of incidence. The albedo for cloud surface average 55%, but it can be up to 80% for thick stratocumulus cloud. The absorption. In our Earth, atmosphere due to the different composition act as a barrier to the insolation, or it absorbs some solar radiation, may be assimilated by the object, is generally termed as atmospheric absorption. The different material on Earth has different absorptivity capability with different wavelength of solar radiation. It is happening in all electromagnetic radiation at certain spectral band by the composition present in the atmosphere. The most efficient absorber of solar radiation in this regard are water, carbon dioxide, ozone, oxygen, nitrous oxide. The cumulative effect of the absorption by the various constituents can cause the atmosphere to close down completely in certain region of the spectrum that lead to an increase in temperature. Generally, a good radiator is also a good absorber and a poor radiator is a poor absorber. As color is concerned, dark color surface are much more efficient absorb of radiation in the visible portion of the spectrum than light color surface, as you can see in the figure number 4. The next is the factor affecting insolation. The actual amount of insolation received by the Earth varies according to the condition of the atmosphere as well as the season. The various astronomical and geographical factors determine the amount of insolation received at any point on the Earth's surface. They are solar output or the constant, angle of incidence, length of the day, Earth distance from Sun, transparency of the atmosphere, solar output. At the top of the atmosphere, Earth atmosphere receives insolation is expressed as solar constant. It received at the top of the atmospheric surface on a perpendicular plane of the solar beam. The average insolation received at the thermopause, that is 1368 watt per square meter energy in the form of short waves. Thus, it is termed as solar constant, for that means distance from the sun. This solar constant is varying over 1 watt per square meter by periodic disturbance and explosion in the solar surface, basically related to sunspot. Sunspot are the dark and the cooler area visible on the sun surface. The recent research have shown that more and more energy is released when sunspots are in large number. The number of sunspots also increases or decreases on a regular basis, creating a cycle of 11 years. When sunspots are maximum, the solar radiation is also maximum. Increase or decrease of sunspot are directly and positively correlated with the received radiation on the energy. On the Earth, it is assumed that our Earth is behaving a black body. A persistent anomaly of 1% in the solar constant could change the mean temperature of Earth's surface by as much as 0.9 degrees Celsius. The solar constant is reduced by half or more through reflection, scattering and absorption of the short wave radiation in the atmosphere. Next is the angle of incidence. The angle at which sun rays strike on Earth's surface is called angle of incidence. It controls the amount of insolation received at the Earth's surface. The amount of insolation is determined by the time of the day, the latitude and season. When the sun rays strike vertically or sun is directly overhead, the rays angle of incidence is 90 degree. The beam of the ray spread on the small area in comparison to oblique or slant beam of sun rays, as you can see in the figure number 5. When sun in a vertical position, the beam of light will spread over 1 mile, but in the oblique position of the sun, the same beam of light will spread over 2 miles. Therefore, per unit area is received energy is greater in the case of vertical beam with reference to oblique or slant beam of the Earth's surface, as you can see in the figure number 6. When sun ray are oblique, it is spread over a relatively larger surface on the Earth, then energy per unit area is decreased. In addition, the oblique ray have to traverse a large distance through the atmosphere before they strike the surface of the Earth. The longer the path, the larger the amount of energy lost by various processes of reflection, absorption and scattering, etc. Thus, it is clear that the longer amount of radiant energy is lost in the case of slant ray than in vertical rays. Therefore, on the average, equatorial area receives approximately 2.4 times more insolation than polar area. Next is the length of day. The length of day is determined the duration of sunlight which affect the amount of solar radiation received by Earth's surface. The longer period of sunshine, greater the quantity of solar radiation will be received by a portion of Earth. For example, at the equator, the length of the day and the night is 12 hours in all the month, but the tropics of Arctic and Antarctica sunshine duration varies between 0 and 24. See the table number 1 showing the length of the day at different latitude on the autumn and spring equinox, that is September 23rd and March 21st respectively. The sun is overhead at the equator at noon. The night and day all over the earth are equal on these days, and maximum amount of insolation is received at the equator, as you can see in the table number 2, and the amount of insolation decreased toward the poles. It is caused by vertical sunshine of equator, but with increasing latitude the rays become more and more slanting. Therefore, poleward the received energy keep on declining. Next is Earth distance from sun. The Earth is revolving around the sun in an elliptical orbit, resulting continuous changes in the distance between sun and the Earth on annual basis. It leads to seasonal variation in solar energy received by the Earth. The mean distance between the Earth and the sun is about 14 crore 96 lakh kilometer. When Earth position is farthest from the sun is known as aphelion on July 4th. The perihelion occurs in January 3rd each year, which is the closest distance. During aphelion, the northern hemisphere is facing the sun and therefore receive energy about 7% less than the perihelion. It appears from the figure number 8. It means that Earth is relatively closer to the sun during the northern hemisphere winter or southern hemisphere summer, that produce an increase in the effective January world surface temperature of about 4 degrees Celsius over those of July. Consequently, northern hemisphere winter is warmer than southern hemisphere winter, and southern hemisphere summer is warmer than northern hemisphere summer. Moreover, southern hemisphere is 5 days less than northern summer. Next is transparency of the atmosphere. Our atmosphere is not transparent for all the radiation coming from the sun because of different composition and layer. It is also one of the controlling factor of insolation to reach Earth's surface. The atmosphere is composed of gases, water vapor and particulate matter. The atmosphere is a mixture of gases such as nitrogen, oxygen, argon, carbon dioxide, neon, helium, methane, krypton, ozone, nitrous oxide, hydrogen and xenon. The atmosphere also contains water vapor in the gaseous state. The concentration of water vapor in the atmosphere are small but variable between nearly 0 and about 5% by volume, usually higher above larger water body. The concentration of water vapor decreases with the altitude from about 4% close to the ground to more or less 0 above about 12 km. The atmosphere also contains a particulate matter which is suspended in the atmosphere. Primarily, the particulate matter are generated by wind blow, minute particle from dry area and desert, pollen and mold spores from vegetation, smokes from natural forest fire and from air pollution, and salt spray from the ocean. All this composition create obstacle in insolation and reinforce the pattern of solar energy distribution at Earth's surface by reflection, refraction, scattering and absorption. Reflection from dust, salt and smoke particle in the air is an important mechanism for returning short wave solar radiation to space. Similarly, reflection from cloud top also deplete the amount of solar radiation that would otherwise be available to the Earth. The transparency of the atmosphere also vary with the latitude. In the higher latitude, the sun rays are more oblique, so that they have to pass through relative thicker layer of the atmosphere than at lower latitude. The next is the distribution of insolation. The total incoming solar radiation is known as insolation. It is always high at pole. In summer solstice, there are two main factors, sun angle and the length of daylight, that influence the insolation in any given location the most. As shown in figure 9, taken by NOAA 19 satellite on July 2012, the highest average daily insolation found over the Arctic because of 24-hour daylight. The absorbed solar radiation in watt per square meter on the same day as figure 4.c taken by NOAA 19, energy absorbed and surface characteristics. For example, land and water determine the pattern of radiation absorption. The Earth's surface receives different amount of insolation according to season. It receives more insolation in summer than winter because of the long day length in higher altitude. The upper atmosphere over the northern pole is marked maximum solar radiation in June solstice, but only 30% of the total insolation is absorbed by the surface due to the high average cloudiness over the Arctic in summer and very high reflectivity, that is the albedo, from the ice surface and snow is compared with the global average of 48% of the insolation being absorbed at the surface. The horizontal distribution of insolation is also varying on the Earth's surface. The maximum temperature is found in the tropics rather than equator because apparent migration of the vertical sun is relatively rapid between 6 degrees north to 6 degrees south. The vertical sun rays during autumn and spring equinox lie for 30 days, allowing very little time span for heating the Earth's surface very high. Contrary to this, the latitude between 17 to 23.5 degree north-south, the insolation occurs almost vertically for 86 consecutive days during solstice. The longer duration of insolation over tropics than at equator makes a maximum temperature zone at tropics, as you can see in the figure number 10. The distribution of land and water also affect the temperature in this zone. In the northern hemisphere, continent enhance the rise of temperature than ocean southern hemisphere. Another factor is cloudiness. In subtropical high pressure zone, due to low cloud cover allow large annual receipt of solar radiation. Now the conclusion. Insolation on the earth is received almost entirely from the sun, which come in the form of electromagnetic radiation from the surface whose temperature is about 6000 K. The solar constant reached to the earth's surface is approximately 1368 watt per square meter. The amount of energy emitted by the sun in the form of electromagnetic radiations receives by the earth is very smaller in comparison to the total energy released from the sun, but it is sufficient to run the earth system and the biotic life involved on the earth. The sun's energy is reaching to the earth is basically solar radiation. There are 5 methods of insolation such as transmission, scattering, refraction, absorption and reflection. These mechanisms impact on an even distribution of insolation in the earth. There are several astronomical and geographical factors that also affect the insolation on the earth. Important among them are solar output, incidence angle of the sun rays, length of the day, variation in distance between earth and the sun, and transparency of the atmosphere. The variation of insolation are also due to the solar flares and sunspot that periodically change the pattern. The varying incidence angle of the sun rays and the length of the day affect the latitudinal variation in the amount of insolation on the earth's surface. Consequently, within the tropics, the total insolation is more than higher latitudes. The distance between sun and the earth as well as the inclination angle of the earth determine the different season on earth. Therefore, uneven distribution of insolation is very important to understand the atmospheric dynamic and distribution of climate and vegetation on earth's surface. The climatic elements such as temperature, precipitation and winds are controlled by the amount of insolation. The livelihood of the people and their comfort as well as plant life are totally depends on the available insolation on the earth's surface. Thank you.